Composition of functions is an operation that takes two functions and produces a third function by applying the first two in succession. Let's just jump right into the definition. If f and g are functions, then the composite function, or composition, of f and g is the function defined by f circle g of x equal f of g of x. The domain of f circle g is the set of all numbers x in the domain of g, such that g of x is in the domain of f. We have to pay special attention to some of the details with this new definition and notation. The name of the composite function is f circle g, pronounced f circle g. If x is the input variable, then f of g of x, or f circle g of x, is the associated output value. The rule for calculating the output value is f of g of x. That is, first we compute g of x, and then input that value into the f function. The expression f of g of x does not represent multiplication. We have to interpret this as composition of functions from the context of the discussion. As usual, let's consider a couple of examples to illustrate this new concept. Suppose that f of x is 2x plus 1, and that g of x is the square root of x. We want to compute both compositions, f circle g of x and g circle f of x. We will apply our definitions. To compute f circle g of x, we use the definition of composition, and the definition yields f of g of x. Now, according to the order of operations, we should compute the innermost value first. Since g of x is the square root of x, we get f of root x. Now we apply f to the input root x by doubling it and adding 1. Therefore, f circle g of x equals 2 times the square root of x plus 1. We still need to compute g circle f of x. Using the definition of composition, we get g of f of x. This time, we apply the f function first. Since f of x is 2x plus 1, we get g of 2x plus 1. Now we apply the g function to 2x plus 1 by applying the square root. Therefore, g circle f of x is the square root of the quantity 2x plus 1. The very first thing we notice is that the function f circle g is not equal to the function g circle f. For many students, composition of functions is the first non-commutative operation that they have encountered. Thus, we have to pay particular attention to the order in which we compose functions. The silly example I like to use is the functions of putting on socks and putting on shoes. It's pretty clear in this example that the order matters. Now let's consider the domain of a composite function. Suppose that f of x is 5 over the quantity x minus 2, and g of x is 1 over x. This time, we want to compute the composition f circle g of x and its domain. Computing the composition will go just as before. To compute f circle g of x, we use the definition of composition and get f of g of x. Now, according to the order of operations, we should compute the innermost value first. Since g of x is 1 over x, we get f of 1 over x. When we plug 1 over x into the formula for f, we get 5 over the quantity 1 over x minus 2. We simplify the complex fraction by multiplying the numerator and denominator by x. This produces 5x over the quantity 1 minus 2x. Now that we have a formula for the composition, we still need to find its domain. We can tell from the formula that x cannot equal 1/2 because that would make the denominator 0 in the formula. However, there may be additional restrictions on the domain due to the composition. From the definition of composition, we know that the domain of F circle G is the set of all x in the domain of G, such that G of x equal 1 over x is in the domain of F. The domain of G is all non-zero x, and the domain of F is all x except 2. Thus, we need all non-zero x such that 1 over x is not 2. The domain of F circle G is therefore the set of all x except 0 and 1/2. Finding the composite functions takes some practice, and finding their domains definitely takes some careful thought. As usual, practicing with a variety of problems is the most effective way to proficiency.